Welcome to lecture 17. In this lecture, we will introduce a new kind of heap called binomial heap. And this heap supports the standard heap operation together with one more operation called union. So first of all, let us recall the binary heap. This is the heap that we have already studied a long time ago. So a binary heap supports efficient insert and extract min operation. In fact, a binary heap also supports the decrease key operation, and this operation can change a value of a certain node to a smaller value. All these three operations can be supported in order of log n time, where n denotes the number of items in the heap. However, there may be cases where we have two different binary heaps and we want to combine all the items in these two heaps together into a single heap. And in such a case, then there is no efficient way of doing so. Because of this, there is another kind of heap, we call it a binomial heap. This binomial heap is a more flexible structure which allows the combining of two heaps. This operation, we usually call it the union operation. With the binomial heap, all the insert, extract min, decrease key, and this union operation can be supported in order of log n time. Now recall that when we were using a binary heap, we are maintaining a binary tree, and we are maintaining just a single tree. But here we will see that for binomial heap, it actually maintains many trees. There could be up to order of log n trees. And because of this, then the structure is more flexible and allows all the operations to be done efficiently. As mentioned, a binomial heap contains a bunch of trees, and each of the tree, we call it a component tree. The component trees inside a binomial heap has a specific format, and each such tree, we call it a binomial tree. So let's see the definition below. Okay, so what is a binomial tree? Okay, so a binomial tree of order k, we denote this by bk, is defined recursively where b of 0 is a tree with a single node. And for larger values of k, bk is formed by linking two bk-1 trees, with the roots of one tree becoming the leftmost child of the roots of the other. So this looks rather difficult to understand, so let's see the example. So this is B0, which contains just a single vertex, a single node. B1 combines two B0 together, joining the roots of one with the roots of the other. And B2 joins two B1s. So there is a B1 here, there is another B1 here. So the root of one of the B1 becomes the leftmost child of the root of the other one. So it is like this. And for B3, you can see that there are two B2s. There's a B2 here, there's another B2 here, so that we are joining the roots of this B2 with the roots of this B2 in this way. The root of a B2 is joined as the leftmost child of another B2. And for B4, we are joining two B3s. So this is a B3 here, this is another B3 here, and then we join it like this. Now it is rather easy to check the following properties of a binomial tree. So for a binomial tree bk of order k, so we have an example of B4 here listed for our reference. The number of nodes in the tree is 2 to the power k. So we can prove this easily by using induction. And similarly, the height counts the number of edges here. The height of this tree is equal to k. So from the root to the farthest away leaf, it's like this, there are 1, 2, 3, 4 edges. So the height of bk is equal to k. Again, this can be proven by induction. The degree of the roots of a bk is equal to k. So for this root here, there are k children. Again, this can be proven by induction. Now, although bk we are defining this using the idea of joining to bk minus 1, another way to see this is like this. So if you look at the children of the root, okay, so the children of the root, this one, each of them is a root of a certain subtree. This one is the root of a b0, this one is the root of a b1, this one is the root of a b2, and this one is the root of a b3. So if we list the child or the children of the roots from left to right, then we will see that there will be a bk minus 1 here, and then a bk minus 2, and so on and so forth up to b0. Okay? And also, let's look at the number of nodes at each level. There will be 1 node at level 0, 4 nodes at level 1, 6 nodes at level 2, 4 nodes at level 3, and then 1 node at level 4, right? So 1, 4, 6, 4, 1. So what are these numbers? These are the numbers of 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. So there will be exactly k choose j nodes at the level j. All these can be proven by induction. Now, because of this property, there is a binomial term here. So that's why we call this tree a binomial tree. Now, what is a binomial heap? Okay, so a binomial heap with n items, it will consist of a set of binomial trees, so that these items, there are n items, so there will be 1 node in this kind of trees corresponding to 1 item. So altogether, a binomial heap will contain n nodes, and these n nodes will form several binomial trees, 1 node corresponding to 1 item. And then the nodes in each binomial tree will satisfy the heap property, where the value of a node will be greater than the value of the parent of the node. And also, we will have at most 1 type of bk for each k. So there will only be 1 bk. If there are 2 bks, then we are going to combine them together into something like a bk plus 1. So there will be only 1 bk at most for each k. Now, because of this, because there is only one way to represent a positive number n as its binary representation, it means that the component trees inside the binomial heap with n items will be unique. So let us see what it means. Okay, so for instance, a binomial heap with 13 items will be having a structure like this. So we don't care about the content. Let's look at the structure. First of all, 13, in its binary representation, it is 1101. So this one corresponds to there is a B0. This one corresponds to there is going to be a B2. And this one corresponds to there will be a B3. So in that case, 13 must always, so if there is a heap, a binomial heap with 13 items, it must always have a B3, a B2, and also a B0. And this is, for the structure wise, it is unique. And also, the nodes itself, it has to satisfy the heap property so that each node will have value greater than that of the parent. So we assume that all the values in all the nodes are distinct. So in that case, so there is no equal. So this one has value greater than the parent. This one has value greater than the parent. Or alternatively, each node must have value smaller than all of its children. Okay, so this is the heap property. Now, because of this, at this point, we can actually see that for each tree, the roots must contain the smallest value. So if you want to know the smallest value of all the nodes in this heap, then it is only the roots that we need to look at. Okay. Now, let us continue with our discussion. So first of all, because the binary representation of the number n has at most log n plus 1 digits, then the binomial heap will contain at most log n plus 1 trees. So it is order of log n trees. And find mean looks at the roots of each tree, so it can be reported in order of log n time. But actually, we can support find mean faster because we can always maintain a pointer that points at the minimum of the current heap. So find mean actually can be done in order 1 time. Okay, now we also see that because each tree bk in the binomial heap has k which is less than or equal to log of n, because the last digit, the maximum digit is only of the, it is going to be the most significant digit is only the at the position of log n away from the right hand side. So we will see that in each of the binomial tree inside the heap, then k has to be less than or equal to log of n. Now, because of the properties that we have mentioned before, the height of the tree is bounded by this k, and then decrease key, so that decrease key can be performed efficiently in order of log n time. Because when we want to decrease the value of a node, let's say we want to decrease the value of this one to a smaller value, let's say 25, we make it into 17, let's say. We just need to compare this one with the parent. If there is nothing wrong, if the heap property is still okay, then we don't need to do anything. But let's say we want to change this value instead to 0, a smaller value than its parent, then we do the swapping. Okay. So for instance, if I change this value to -1, then I swap with this one. Now -1 will be here, then I will swap with this one. -1 will be here, I will swap with this one, and so on and so forth. So decrease key can be performed by swapping a node with its parents repeatedly to fix the heap property. It is just like the insert operation in a binary heap. Okay. So the time taken is bounded by the tree height, and because for each binomial tree k is less than or equal to log n, so the tree height is bounded by log of n. So in that case, decrease key also can be performed in order log n time. Now, to perform union of two binomial heaps, let's call it h1 and h2, we will process their component trees so that we are going to merge two. So we are going to process their component trees in a certain order, actually from the smallest k first to the largest k, okay, from small order to large order. And what we do here is that when we see two trees bk with the same order among the combined heaps, we will link them so that we will link the roots of them together to form a bk plus 1. Okay, so how do we link them? That's easy. So we will link the one that has the smaller value to become the new root, and the larger value will become the leftmost child. So let's see an example. So this is h1, this is h2. What we are doing here is that we are going to process the component trees from the smallest order to the largest order. So h1 has this one, h2 has this one, and they are having the same order. They are b0, right? So we are going to combine them. So when we merge them together, we link the roots. This one has a smaller value, so this becomes the new root. So after one step, we will have this one. We are linking to b0. And now b0 is done, so it becomes a b1. And this is the only b1 in the system, so we don't need to do anything more. And now we have a b2 from h1. We have another b2 from h2. So with two of them to be the same, we link them. This one, the root has smaller value. This one, the root has larger value. So this becomes the subtree linked on the left-hand side of this one. So like this. Is that okay? So we are linking two b2s now. Now, after the linking process, we will have this one a b3 and also another b3 originally that is present. So we are going to link the two b3s together. So we link the B3s. So in that case, 8 will become the new root, 15 will become the leftmost child of this 8. So we will have this one. Okay. So in that case, union actually can be performed by processing the trees from small to large, so that altogether constant time per tree, so altogether order of log n time. And this operation is just the same as we are adding two binary numbers. Now, when we want to insert an item into an existing heap, what we do here is that we apply the union operation as a subroutine. First of all, we create a heap H prime with a single tree B0 containing the inserted item X. So we now have the original heap H and the new heap H prime with a single node. Then in that case, we call union. So inserts can be done by taking constant time to create this single node tree B0 and then log n time to do the union. So inserts can also be done in order log n time. Now, how about extract min? So extract min is also very easy, okay? So when we perform extract min, first of all, we find out which node is the current minimum. So it must be a root node of some tree bj. Okay. After that, what we are going to do here is that we isolate this tree containing the minimum node from the remaining heap. So this is easy. Just we take out one tree completely from the existing heap, so it can be done in constant time, so that the original heap becomes H1. And next, what we do here is that at this moment, we have not done any extract min operation. We just isolate a tree from the original heap. But next, we are going to remove the root node of Bj. This is the minimum of the current items. So we remove it. Now, when we remove the root of this Bj, then Bj, the remaining part will be a bunch of trees. Okay, so it will become another heap of H2. So it has J component trees. After that, we will have H1 and H2. We perform a union of them. So we need to get back what we want. So let's see. So this is actually a very simple operation. Let's see. So here, let's say this is the current heap H. And then by looking at the nodes of the root nodes, we will find that this is the minimum, right? So this is the Bj that we are going to isolate. So at the first step, we isolate this Bj, and then so H becomes H1, and then the Bj becomes here. But what we do also next is we are taking away the root node of this one. So taking away the root node takes away all the edges that it connects to. So in that case, the remaining parts will be separated into children subtrees of this root. So there will be J subtrees. Is that okay? In fact, this is also a heap. Is that okay? And after that, what do we do? After that, we are just doing the union operation. So when we do the union, this one and this one has degree 0. So B0, B0 join together. And then, yeah, I'm doing this very quickly. So you see that I have done a lot of steps together. So we are going to join these two. We get a B1. This B1 is joined with this one. We get a B2. So after that, nothing else is done because it is a B3. So after the steps, we will have this 12 here, joining 13, and then we will have this original B3. Okay. And finally, we will see that we can also support an extra operation called delete. So delete is an operation that we want to point at a certain node, and then we want to remove this node or this item from the heap. So how do we do? Okay. So when we want to remove a certain item X from the heap, then we perform decrease key on this item X, setting the value to be minus infinity. After that, after this decrease key operation, this must be the node with the minimum value. So we call extract min. So deletes can be performed by doing decrease key and then extract min. Because both operations run in order log n time, so delete can be done in order log n time. So that's the description of this binomial heap data structure. Thank you.